Okay, grade 9. So this is January 4th week. We're going to be starting space exploration. I'm going to give you basically about an hour's worth of material for the whole week, which works out to be, less than 15 minutes per day. So you have the booklets, Unit 4 Space Exploration, Topic 1 for Our Eyes Only. Okay, and so here it space, one of my favorite units. There's not a lot of lab work. There's 4 or 5 labs that we could do, and I really hope after the 11th we're back together, and that's why I chose this one to start with. The textbook does a pretty good job of outlining what you need to know in this unit. Like the biology and the chemistry were super essential for high school. This one's got lots of cool stuff in it, got some physics in it as well. A lot of other teachers just get people to read the book, but I love the space unit, so I spend more time on it than the average teacher. Why don't we usually spend a whole bunch of time as science teachers? Probably because not a lot of us took astronomy classes, so really it's got to be a personal interest that draws you into this. So here we go. Here's a picture looking at the Earth from the moon, and whether you're on the Earth or the moon, you feel that the ground below you is stable. Okay, so that means that you have different frame of references. Okay, and when we look into space, it seems as if the sky is traveling around the planet, but we know what's really happening is that the Earth isn't moving. Well, the Earth actually does move, but when we see the skies travel, it feels like the Earth is stationary, and it looks like the universe is turning above us, but it's actually a combination of the Earth is turning, the Earth is also moving around the sun, and our galaxy, our galaxy is moving relative to other galaxies, which is moving in directions relative to this whole universe. So Mr. Tierra sitting here at a desk is not stationary by any means, okay? But it depends on where you do your frame of reference. I mean, you can get some funny stuff too. I saw in the summer a housefly going 110 kilometers per hour. Now, it was in my car, so it was going 110 kilometers relative to the ground. But relative to me in the car, it was sitting on the dash, it was moving 0. So it really depends on what your frame of reference is when you describe the motion or the position of something, for that matter as well. Right? I could say I'm in Strathmore, but Strathmore is slowly turning as the Earth rotates, and it's also the Earth is going around the sun. So my distance relative to another planet is constantly changing. But from my point of view right now, I'm sitting in Strathmore, I'm not moving, so my velocity is 0. Okay, and so a frame of reference is a set of axes of any kind that's used to describe the position or motion of things. We have the equator and prime meridian are axes for our frame of reference, longitude or latitude otherwise. If you're riding on a school bus going 100 kilometers per hour, that's relative to the ground. Your velocity relative to the school bus, though, would be 0. Okay, so really what you're seeing and experiencing truly depends on your frame of reference. Now, because I am doing this as a YouTube video, I can't show you any of my videos. I could post a link to them, but as soon as I try and play a video, YouTube gets kind of mad at me. I mean, I could try. I don't know how well this is going to turn out. Let's give it a try. Here.
their perspective was different than my perspective. Hi, I'm Gus Savano, and today my friends and I are going to teach you about frame of reference.
The way you see your world is called your perspective. But sometimes your perspective isn't always where it needs to be. That's why you can't tell what you believe your eyes.
Hey, can I have some of that? Sure. Thanks. Sure. Is Greg really spinning, or is it the camera in the back? If you guess B, then you're correct.
Another example is, it doesn't actually look like I'm driving when I really am.
And in this case, I'm not actually driving. Relative to me, Davis isn't going very fast.
But to a bystander, they're both fine. Well, Davis isn't.
Hopefully, through this video, you've learned just why perspective and our frame of reference play such a big part in our lives. And that, my friends, is how the cookie crumbles. Oh, this
It'll be interesting to see if they let me keep that posted. All right, let's look at some more frame of reference. So here we go, vector addition frame of reference. When trying to determine the resultant velocity in frame of reference questions, you're always trying to describe some sort of motion relative to a fixed non-moving frame. You then draw arrows showing the direction of movements and size. So a large arrow is a large movement, small arrow is a small movement. Then you add or subtract based on your direction. You don't have this worksheet with you. I will post it with the link for this, so you can you can print it off, or you can just write it down on a piece of paper. So first question says, Billy Bob walks at 1 meter per second towards the head of an alligator who is swimming at 3 meters per second. How fast is Billy Bob appeared to be moving the first amount of time? So I'm going to draw a quick picture. I need an alligator. There's my alligator. I need Billy Bob walking towards the head of an alligator. So he is on the tail walking towards the head of the alligator. So to find the resultant, you actually have to draw arrows. Okay, so the alligator is going at 3. So the alligator is going forward at 3. Billy Bob is also moving forward at 1. So someone who's standing on the shore watching this float by would see Billy Bob go by at 4 meters per second towards the right side. Right? Because the alligator is moving and Billy Bob's moving on him as well. So if they're going in the same direction, you add the vector. Now, Billy Bob is going to start to run at 3 meters per second towards the tail of the alligator. So I need my alligator again. alligator's angry now. So the alligator is swimming forward at 5. So it's going this way at 5. So a nice big arrow to show the 5. And Billy Bob is running towards the tail. He's going back 3. So that means every second, what is he doing? Well, relative to the the ground, someone seeing it, if they could just see Billy Bob, he would look like he's going 2 meters per second. But he's still going right because the alligator goes 5 this way, and he only gets pulled back, runs back at 3. So it's still going towards right. So it's actually just like adding and subtracting integers. If they're going in the same direction, you add them. So if they're both pluses, you add them. If they're plus and a minus, you subtract them. And the overall integer is determined by the largest number. In this case, the overall direction is determined by the largest vector. Let's try another one. Bobby Sue is riding in a car traveling north at 80. So the car is going north at 80. And I'm just going to label this north and south. And then she throws a ball out the window, but she throws it backwards. She throws it south at 20. The question is, how fast does a note look like it's going to Mr. Tierra, who is standing on the side watching this? Well, if I'm standing on the side watching this, I see the car go by at 80. I see her throw the ball backwards at 20. So they're going in opposite directions. So it's going to be 60 kilometers per hour. And then the biggest arrow determines the overall direction, which the biggest arrow is this one. So it's going to be north. Now, Bobby Sue gets into trouble. Her parents are driving 100 kilometers per hour south to get the ball back. So here it is. Bigger arrow going 100 kilometers. I'm going to label it south, and this is north. Bobby Sue writes an apology note and throws it out the window south at 5. The question is, from my frame of reference, how fast does it look like that note is going? Well, they're going in the same direction, right? So they're going to add up. So it's going to be 105 kilometers per hour towards me, or if you want, south. All right, let's look at some more. It's the Bugs Bunny worksheet. So here it is. If you want, you can pause the video and try these questions out, and then you can unpause the video and get it to play. I'm just going to draw my truck while I'm waiting. Bugs Bunny, it's usually grayish in color. But he's usually only a carrot. So there's my carrot. It looks a little bit more like a lightsaber. But there's my Bugs Bunny traveling on a truck. I suppose the truck should have a front window, maybe a stack on it as well. And then it's going 100 kilometers per hour west. So 100 kilometers per hour west. I'm going to call that side west, the other side east. Okay, so the first question says, and of course, pause it and try these out so you know how to do them. What's the speed and direction of the truck relative to the ground? Well, relative to the ground, it's going 100 kilometers per hour, and it's traveling west. B, what's the speed and direction of Bugs Bunny relative to the ground? Well, Bugs Bunny relative to the ground is also going 100 kilometers per hour west. In parts A and B, what is the frame of reference? So how are we describing the speed of each of these relative to the ground? So the ground is your frame of reference, right? Pretending the ground's not moving. What's the speed and direction of Bugs Bunny relative to the truck? Now, Bugs Bunny is standing on the truck. So it's like if you're filming, how fast does it look like you're going if you are filming and centered on the truck? Well, Bugs Bunny would not look like he's moving relative to the truck. It would be 0. He's moving relative to the ground, but not relative to the truck. Next one, there's a highway marker sign west of the truck. How fast does the sign appear to be moving relative to the trucker? So here's where it gets interesting. The truck driver sees the sign. Is the sign moving towards him or away from him, it's moving towards him. And so how fast? At 100 kilometers per hour towards him. Technically, he does not have an east or west, right? And so from his frame of reference, he's seeing the sign moving towards him. After he passes it, what does he see the sign doing? He sees it doing 100 kilometers per hour away from him. Question is, how fast is the sign moving relative to the ground? Well, the sign is, posted in the ground, so it's going at 0. If Bugs Bunny starts running at 30 kilometers per hour east and the truck is moving 100 kilometers per hour west, how fast is he moving relative to the ground? So the truck is doing this, 100 west, and he starts running around at 30 east. So he's coming back 30. How fast does it look like he's going? Well, they're going in opposite directions, so you're going to subtract them, right? So 70 kilometers per hour, but the biggest arrow determines the direction. So it's going to be west. And there's another one. I just can't seem to see it. Let me just go to full screen and I'll be able to see it. Bit to height. Bugs Bunny starts running that east. There's one more. No. I should get better with computers. Very embarrassing. All right. Let's see if I can do this again. How about if we do this? No. The other one has them both moving in the same direction. And so I believe it's 100 kilometers per hour west, and then also Bugs Bunny is going 20 kilometers west. So if they're going in the same direction, then like 100 kilometers west, and I think it's another 20 kilometers west. He's running towards the front of the truck. That would place him going 120 kilometers per hour towards the front of the truck or in the westward direction. So eventually he will be running fast enough that he would be able to go off the truck. This is from the bottom of the page.
Grade 7, return to class.
Okay, so in your notes, there is a page 2 and a page 3 assignment. Okay, so this one is going to be for Mark. So I'm going to go ahead and get you to do that right now. Okay, so that assignment should take you about 10 minutes or so. So I'm just going to put that in here. Let's see if I can do this. Insert page, tools. So insert text. Here we go. Do page 2 and 3 in the space. This should take 15 minutes and is due when we return. Okay, and so that would be the 30-minute lesson for today. So you're doing that right now, and you can pause this video. I'm supposed to do 2 30-minute videos, so you can pause it, and you're doing that, and I am going to go into continue on in the notes. Okay, so what?
Grade 8, this is the start of your break.
What our ancestors saw. So the old view that the stars revolved around the earth, ancient people learned many things about the motion of celestial bodies. stars making unchanging patterns in the sky. These are called constellations. Okay, Orion, the Hunter, Ursa Major, the Great Bear. On each successive day, a given star rises and sets 4 minutes earlier. This helped people predict changes of seasons and and led to the creation of calendars. Okay, and so here are some things that they saw. They saw that the sun rises and sets at a different rate from other stars. They also saw that the moon rises and sets at a rate different from stars and shows phases as well. They didn't fully understand why yet. They also saw 5 other bodies, Mercury, Venus, Mars, Jupiter, and Saturn, rise and set at different rates from the stars. The ancient Greeks called these wanderers, and the Greek word for wanderer is planet. I don't know if they planned it that way. It's not the same doing bad puns without people, live audience. Here is an awesome example of a calendar. So that's Stonehenge. Maybe some of you have seen it. I haven't seen it yet, but it's on my list of things to see at some point in time. You stand at the center and you look out, you can predict when the seasons are coming. My son also told me that if you stand at the center or at different parts of it, it acts as a sound amplifier. So there is that aspect as well. Who built it? I mean, that's up for debate. So, we have evidence to indicate that the rocks traveled from 500 kilometers, so they must have had really good technology to move it there, and they must have had a really great need for a calendar in order to build it. I mean, the alternative explanation is that aliens came down and placed them there, kind of like probably as a joke, and to confuse people for thousands of years. It was constructed sometimes between 3000 BC and 1000 BCE. Some other ancient myths. Many ancient societies created their own stories, okay, like to explain the origins. And by telling stories, it's easier to remember what's going on. So I mean, I tried to do a little bit of that in science. So the Romans thought Jupiter was the king of the gods. The Egyptians thought the sun god Ra was carried across the sky daily in a boat. Interesting about that one, that shows up in a lot of trivia games. The Aboriginal people in North America had their own myths. Ursa Major was a bear running from the hunters. The bear is low enough to brush the maple trees in autumn. The blood makes the leaves red. Another group tells a legend of 3 hunters chasing 4 elk. It becomes 7 stars of the Big Dipper. So I'm going to try playing this video as well, and we'll see if I get, if they allow it. I'm not making money off this video, so I should be allowed to play the video, but let's see.
So this story concerns the asterism known as the Big Dipper. For a lot of First Nations people, this story represents the greatest animals. And the foremost among them is the big bear. And then the Cree language is called Mr. Muskwa. The legend talks about what the wages of being a bully are, and how even the littlest of animals can bring down the most ferocious. The way the story goes is that long ago there was a big bear which roamed the country, and this bear was the hugest, of course, biggest, the meanest, and therefore it did what it wanted to do. It preyed on everybody, every spiritual being on the face of Mother Earth. And this went on for years and years. The bear stole winter supplies, ripped up camps, killed spiritual beings, killed the animals, killed humans. And so one day, all these beings had a big meeting, and they decided that they were tired of being afraid of this bear. And so it was decided that the bear would have to go. 7 hunters were chosen, 7 of the best trackers, and 7 of the best shots. Small birds were sent to do away with this bear. They went hunting for the bear, but the bear was forewarned by a raven and a crow that there were hunters after him. And so the bear, upon hearing that he was being hunted, took off, and the birds chased him. And the way the elders say is that the chase was on, and it went around the world 4 times. It circled the globe. And on the 4th time, they were going so fast that they came up over the horizon, and they flew into the air. This happened to be just around September, October. And as they flew into the air, the bear saw that the hunters were gaining on him, and he was getting tired, so he turned and he faced his attackers, his hunters. And just as he did that, one of the lead birds got a shot and mortally wounded that bear. So that bear was bleeding profusely as he stood and faced his hunters. And he shook just like a dog shakes when it's wet. And as he shook, all the blood he was bleeding fell to the earth and landed on all the broadleaf plants. So that's why I always say that in around September, October, all the leaves change color because of the blood of that bear. They also go on to say that when that bear shook, a droplet of blood hit that lead bird, the one that shot the bear right in the chest. And today he has a red breast. And for the Cree people, they call that bird pee-pee tail, the robin. And that's why the robin today has a red breast. And so they got rid of that bear to forewarn everybody about the wages of being a bully, of abusing your power. That big bear was put in the sky. And also to honor those 7 birds, they placed those birds in the sky, right in front of that big bear. That lead bird, pee-pee tail, is the brightest star in that constellation. And that pee-pee tail, the robin, was also given a special egg, and that egg represented the color of the sky. And on that egg, there were speckles to represent the Tawasak, the stars. And that's why our elders always warn the children never to harm a robin, because it's a special bird. It's a creator's bird. And that is the legend of Mr. Muskwa, the big bear.
Okay, and every culture has their own stories, which is pretty cool. Also, one last thing. You did the assignments now, and so you truly understand. Is it possible to be riding on a truck and to take a ball? Let's say a truck is going forward at 50 kilometers. Can you throw the ball backwards and have it stop in midair and fall straight down? So the velocity of that ball is 0 relative to the ground. Well, if the truck is going plus 50, if you can throw that ball back at 50 as well, then the 2 speeds should cancel out and it should drop to the ground, just like in this video from the Mythbusters.
Can an object shot backwards while traveling forwards ever drop straight to the ground? It's a fascinating thought, but trying to prove it is bringing our physics team unraveled. Tori, Carrie, and Grant are struggling to prove the supposedly common sense myth that an object drops straight to the ground when its forward and backward momentum are exactly the same. With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, that looks pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh no, it's like a cartoon. It's just an air, stop, it's just fall.
Look at that. Hey, I mean, look, it doesn't do it all. It's going straight down.
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard work.
Grade 8, return to class.
Okay, and that is 30 minutes of science. So I'm going to post another one, still outcome 1, so part 2. That'll be another 30 minutes, and this will be enough work, plus 1 Google form for the 1 hour work for January 4th to the 11th. So stay tuned. Watch the next video right away if you want to.